Here's your 5 a day. And here are the answers. This lesson is on the Euclidean algorithm. Okay, so if we've got two integers with one of them greater than 0, then there are two other unique integers such that we can write this relationship, where our remainder is positive and less than a. Q, to kind of make this a bit easier, so a and b are the integers that we're talking about. Q is for quotient, R for remainder. Let's have a look at how we might do that. So negative 64 is 7 times, I have to think what's the biggest thing I multiply 7 by that I can then add something on to get to negative 64. So this gives me 7 times negative 10, which is negative 70, and then add 6. I need this number here, remember, to be between 0 and 7. I can't choose negative 9, as then this gives me a subtract 1 here, a negative 1, and my remainder is less than 0. Now, if we have b equals aq plus r, then the highest common factor of b and a is the same as the highest common factor of a and r. If b is the multiple of something and a is multiple of something, then the difference between them must also be a multiple of that thing. That's what this is based on. So let's have a look at how we can use the Euclidean algorithm to find the highest common factor of these two rather large numbers. So I'm going to start by writing 3,875 equals something times 1,271 plus something. I can see that it's 3 times this, and my remainder is 62. Now I take my 1,271. I'm now going to be looking for the highest common factor of 1,271 and 62. So 1,271 is equal to 20 times 62 plus 31. So I'm now looking for the highest common factor of 31 and 62. 62 is equal to 31 times 2 plus 0. But no remainder there, so I stop. So what I can say is that the highest common factor of 31 and 62 is 31. And then I can work my way back up these statements to say that the highest common factor of these two, in my two original numbers, equals 31. It's really important that you set your working out clearly here. So if you use this, I've actually written my Q and then my A. It doesn't matter which way around you write it, but as you move your way down, make sure that this is always the Q and this is always the A, or vice versa. Okay, so pause the video now and use the Euclidean algorithm to answer questions 1 to 3. Now, the Euclidean algorithm is useful because we can use it to solve linear Diophantine equations. So here's our example question. Now, if you were solving this the previous way, we would have divided through by 2 first, but we're not going to do that here. So we're going to write 22 equals 3 times 6 plus 4. I'm calling that equation 1. 6 equals 1 times 4 plus 2. And last step there. Now I know you could find the highest common factor of 22 and 6 without using this algorithm, but it's this process, it's these relationships that you're finding here that are going to be useful to you. Okay, so our highest common factor is 2. So now I take equation 2 and I subtract the 1 times 4 from both sides. It's important that we write it as 1 times 4 and not just 4. Now, this 4 I rewrite using equation 1, where I subtract 3 times 6 from both sides. Now I'm going to expand this bracket. So that's negative 1 times 22, negative 1 times negative 3 times 6. And now I've got a 6 here, plus 3 times 6, so that's 4 times 6. And notice I've got a 6, I've got a 22. And I can check negative 1 times 22 is negative 22, plus 4 times 6, which is 24, gives me 2. So that's one solution to my equation. The other solutions, remember, to find the coefficients of t for the other solutions, I need to have divided through by the highest common factor, which is 2 in this case, we found it here. And here are my general solutions. So negative 1, plus 3t, which is plus 6 over 2t, and then 4 minus 11t minus 22 over 2t. And as always, it's really important to state that t is an integer. So now you can have a go at question 4. Thank you.